time. And that's a lot more. So this number here, the number of different fields, will be vastly, 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 vastly more than there were if you had a small number of dimensions. And it's very hard to see how you can make a theory like that look anything like an ordinary physical theory, where you have a theory where D is a 3 up there. So that's the sort of reason that I'm interested in this kind of thing here. Now, one of the things you might say is, well, if you're looking at a theory which is a quantum mechanical theory, maybe the rules are different. In fact, they are a bit different. And one of the good uses of this kind of scheme is, in fact, in thinking about the very earliest piece of quantum mechanics, actually, the very earliest of all, which had to do with Planck's original step, which started quantum mechanics, and it's the Planck spectrum. This has to do with what's called black body radiation, and here we have, well, the sort of thing was like this. You have some kind of an oven where you heat, you just heat what's inside it, and here's a little peephole, you see, so you can imagine you're looking in. It's not done quite like that, of course, but basically what you have here is matter and radiation in equilibrium. Now, there's a thing called equipartition of energy, which tells you that if you have a system in equilibrium, then the different degrees of freedom of that system, the amount of energy goes equally into each of these different numbers of degrees of freedom. But here you have, what have you got? You see, classically, you think of a lot of particles and a continuous field. Now, each of the particles, you know, there could be a certain number of particles, and the number of degrees of freedom it has, well, each one will have 3 or 6 or whatever it is. And if there are a certain number of particles, well, then the B in this expression will be a finite number. Whereas if it's a field here, you have something like Wheeler's infinity to the k to the infinity to the 3, which is vastly more. You see, in this case, the 3 up there has gone to 0, or gone to 1. Sorry, it's not a 0, isn't it? 0. So this number is vastly more than that, and this is what's called the ultraviolet catastrophe, according to Ehrenfest, because there are infinitely more degrees of freedom in the continuous field than there are in the particles, no matter how many particles there are. So therefore, the energy will get drained completely out of the particles and go into the field. And so that isn't what happens. And to understand what does happen, Planck had to introduce his famous formula that the energy in a field of frequency nu can only come in bundles of h, that's the Planck's constant, times that frequency. And with that idea, he managed to explain this wonderful curve, which gives you the intensity for each frequency. And that's what's found, not the answer that you would expect if you had a classical theory like this. So that in some sense, the field behaves like particles, so that there's more of a trade-off between the field and the particles. But the catch to this, which is a sort of feature of quantum theory or quantum field theory, is that the number of particles is not a definite number. It could be more and more, and it could be more or less. And you are now comparing things which are all a great jumble, you see. You have lots of particles or fewer particles, and if you've got more particles, then you've got a bigger number up the top here. If you've got, see, you might have a 3. In fact, I should explain a bit more what you do. You see, this is a thing called phase space. Let me say a little bit quickly about this is configuration space. This is a very important notion, which also I have to come back to later, that if you want to describe some very complicated system with lots and lots of things in it, there's a very nice way, important way you do this in physics, which is to construct a space. I can't draw it very well because it's got a huge number of dimensions, and what you do is you just take all the different numbers you need here to represent how everything is arranged, or if they're just points, you need 3 numbers for the point, but they could be some rigid body like some of these other things, and then you need 6 numbers for the point. But it's just a certain number of numbers, and then for all of those, each coordinate you need another dimension. So this is a huge number of dimensions of space, and any point in this huge configuration space represents everything over here. So all the different ways this thing over here can be arranged is simply represented by a single point in a space of a large number of dimensions. And if they were n structureless particles, let's forget all the rigid bodies and all that, and n structureless point particles, then we have 3 to the n dimensions. So that's the number of dimensions of the configuration space. But in physics, one's usually interested in something a bit more than that, because if you want to know what this thing's going to do, you need to know not just where they all are, but how they're moving. So what are the velocities, if you like, what are the motions of everything? And if they're point particles, you just need to know which direction they're moving and how fast. And if they're more rigid things, you'd have to know how they're spinning and things like that too. So I've considered now what is called phase space now, not configuration space, which is what you get when you think of all the motions. And in fact, you usually describe these motions in terms of what's called momenta instead of the velocities. So you take into account the mass of the objects as well as the velocities. Mass times velocity gives you the momentum, and that's what you need to characterize the motion. That doubles the number of dimensions of this space here. So instead of having 3 to the n dimensions, you have 6 to the n dimensions. So that's the sort of thing you need for n particles. Okay, so that's what you need to characterize individual. But it's still a finite number, you see. Maybe a huge number, but it's still a finite number. So you're comparing infinity to a finite number like that with something with you've got an infinite number up here. And so that's why everything drains off into the into the field, because that's actually a much bigger number than that one. But in quantum field theory, it's not a definite number, so you might have more and more and more particles, but if you've got more particles, then you have to divide the energy up more, and so you have to worry about this formula here and how you can do it. So it's a slightly complicated problem to work out exactly what the distribution is going to be, but you can work out what this curve is like just from that sort of information. So it's a very basic thing. In fact, so basic that it's what started quantum mechanics off. But it does have the sort of property that you have to worry a little about these formulae here and how you compare them, because you can have... Basically what's happened is when you have this Planck formula, you have a kind of... It's a little bit like going back to my previous transparency, if I can find it, which is one would be... I should have kept my glasses on because it's hard to see in the dark here. This one here. See, I should have kept... we have n here. If we kept n rather than infinity, you see, that's a bit more like what happens in quantum mechanics, because this is a very big number, but it's not infinite. So you can still compare these things with each other. It's just that they're liable to be much larger if you've got a big exponent up the top here. Just that, that it's not exactly that they will always be larger. So you have to be a bit careful about the arguments. Nevertheless, it doesn't make a huge amount of difference, and you can't get away with having a d which is too big just by appealing to quantum mechanics.